To understand the machine, one must first understand the era that demanded its creation. It was the twilight of the Cold War, a period defined by a silent, screaming tension that stretched from the gray waters of the North Atlantic to the thin, frozen air above the Bering Strait. The philosophy of the time was dictated by a single, ruthless metric: air superiority. In the strategy rooms of the Pentagon and the grim, concrete bunkers of the Soviet High Command, the logic was absolute. If the balloon went up, if the Cold War turned hot, the side that controlled the skies in the first 24 hours would control the destiny of the world for the next century. This belief drove a frantic, almost religious pursuit of engineering perfection. It was an age of aluminum and titanium, of burning kerosene and raw thrust, where the limits of human physiology were merely obstacles to be engineered around. Into this high-stakes arena stepped a new contender. In the late 1970s, a consortium of top-tier defense contractors unveiled a blueprint that promised to rewrite the physics of aerial combat. The project was shrouded in layers of classification so dense that even the test pilots assigned to the program were initially briefed only on need-to-know handling characteristics. This was the Interceptor X, a designation that would change half a dozen times before production, and on paper, it was a masterpiece. The engineering of Icarus. The design brief had been a paradox. The Air Force wanted a ghost. They wanted an aircraft that was lighter than its predecessors, stripping away the heavy armor and redundant hydraulic systems of the Vietnam era. Yet, simultaneously, they demanded a bird that could carry a heavier payload of next-generation avionics, radar-guided missiles, and electronic countermeasures. They wanted a featherweight boxer with the punch of a heavyweight champion. The engineers responded with a fuselage that looked like it was moving even when it was parked on the tarmac. It was a dagger of polished metal, featuring swept-back wings and massive dual intakes that gulped air to feed an engine so powerful it accounted for nearly 40% of the aircraft's total length. Every inch of the airframe was optimized for speed and agility. The drag coefficient was whittled down to numbers that made aerodynamicists weep with joy. The thrust-to-weight ratio was greater than 1:1, meaning the aircraft could accelerate purely vertically, climbing straight up into the stratosphere like a rocket. But the true revolution wasn't the skin, it was the nervous system. This was the dawn of the digital cockpit. The designers were moving away from the purely mechanical linkages of the past, cables and pulleys that physically connected the pilot's stick to the ailerons, and stepping into the brave new world of electronics. The jet was packed with miles of wiring, sophisticated fire control radars, and systems designed to manage the unstable flight characteristics that gave the plane its maneuverability. When the prototype finally rolled out of the hangar for its debut, bathed in the harsh glare of floodlights, it looked like the future. Generals nodded in approval, senators calculated the jobs it would bring to their districts. Pilots looked at the sleek canopy and imagined themselves at Mach 2, ruling the edges of space. They saw the speed. They saw the power. What they didn't see, what no one saw, because it was buried beneath panels of riveted aluminum and tangled wire, was a flaw. It was a ghost in the machine, a tiny, innocuous intersection of engineering oversight and ergonomic failure that would turn this technological marvel into a flying coffin. To step into the cockpit of a Cold War fighter jet is to step into the most expensive, claustrophobic, and complex office on Earth. In modern fifth-generation fighters, information is consolidated on sleek, multifunction glass touchscreens. But in this transitional era, the cockpit was a chaotic clutter of steam gauges, analog dials, toggle switches, circuit breakers, warning lights, and knobs. There were literally hundreds of tactile inputs surrounding the pilot. Every square inch of the side consoles, the main instrument panel, and even the space behind the pilot's elbows was occupied by a control mechanism. This environment was known as the Iron Works. It smelled of ozone, sweat, rubber, and hydraulic fluid. It was a place of sensory overload, where a pilot had to process altitude, airspeed, angle of attack, fuel flow, radar returns, and threat warnings simultaneously, all while pulling G-forces that tried to drain the blood from their brain. In this dense forest of controls, standardization was the only thing standing between a pilot and disaster. This concept, known as switchology, dictates that critical systems should be easily accessible and distinct, while maintenance systems should be guarded or placed out of reach. The designers of this new interceptor, however, had made a critical error in their geography. The switch, on the right-hand console, Nestled among a bank of essential controls for the environmental systems and the radio, sat a small, rotary selector switch. It was unremarkable. It was black, roughly the size of a bottle cap, with white detents clicking into place around a central axis. The label, etched in glowing radium paint, read, Meter SEL. Its purpose was purely diagnostic. It allowed the ground crew, or the pilot during a pre-flight check on the ground, to route the signal from the aircraft's main electrical bus to a specific gauge on the dashboard. By rotating the switch, one could check the voltage of the battery, the amperage of the generator, or the continuity of the weapon circuits. It was a maintenance tool. It had no business being touched during flight. In a logical world, this switch would have been placed under a safety cover, or located on a breaker panel behind the seat, accessible only when the aircraft was powered down. Instead, the engineers had placed it in the prime real estate of the right console. The anatomy of a trap. The placement was the first sin, the wiring was the second. The Meter SEL switch was not an isolated system. To save weight and reduce the complexity of the wiring harness, a constant obsession in the design phase, the switch was integrated into the main power distribution grid. Here lay the dormant catastrophe. One of the positions on this rotary switch was labeled test. When selected, it was designed to send a high-voltage pulse through the system to verify the integrity of the indicators. This was standard procedure, on the ground. However, the wiring diagram revealed a horrifying adjacency. The circuit controlled by the test position ran parallel, separated by only millimeters of insulation and a single relay, to the fuel transfer and jettison system and the Ordnance Master Arm bus. The flaw was a sneak circuit, an unintended path for electricity to travel. If the switch was rotated to the wrong position while the main generators were online and the engine was at high RPM, creating a massive electrical load, the voltage wouldn't just test the gauge. It would arc. The muscle memory of death. The tragedy of the design was how it interacted with the pilot's body. In the heat of combat, or during the violent buffeting of low-level flight, a pilot does not look at their hands. They fly by, blind cockpit drills. They know that the radio volume is here, the flap lever is there, and the oxygen regulator is here. The Meter SEL switch was located approximately 3 inches forward of the IFF identification friend or foe dial and 2 inches aft of the cabin temp knob. Imagine a pilot at 20,000 feet. He is dogfighting. He is pulling 6 gigaseconds, his body weighing 6 times its normal mass. His helmet is slammed against the headrest. He is sweating profusely. The canopy is frosting up, and he reaches down blindly to adjust the cabin temperature to clear the glass. His gloved hand, heavy and shaking from the vibration of the airframe, fumbles along the right console. He feels a rotary knob. His brain, starved of oxygen and focused on the MiG in front of him, registers the shape. Click. He doesn't turn the temperature knob. He turns the meter selector. He rotates it past the safe zones. He rotates it into the test detent. The spark. The result was instantaneous and catastrophic. Deep in the bowels of the fuselage, the high amperage current intended for a test gauge jumped the gap. It bypassed the safety relays. It surged into the fuel management system. In some cases, this caused the fuel pumps to reverse and overheat instantly, turning the volatile jet fuel vapor in the lines into a bomb. In other variations of the failure, the surge triggered the explosive cartridges in the ejection seat or the ordnance racks. The pilot wouldn't even have time to realize his mistake. One moment, he was flying the world's most advanced Predator. The next, a rogue electrical arc was rewriting the laws of his survival. The aircraft would shudder, the electrical panel would light up like a Christmas tree in its final death throes, and then, oblivion. It was a booby trap built by the best minds in aviation, a landmine hidden in the dashboard, waiting for a single, clumsy thumb to detonate it. The pilots who survived the early near misses coined a grim phrase for the cockpit layout. They didn't call it modern. They didn't call it advanced. They called it the electric chair. To the uninitiated, electricity is instantaneous. You flip a switch, the light turns on. But in the complex, high-impedance nervous system of a fighter jet, electricity is a fluid. It flows, it pressures, and if given the wrong path, it floods. The fatal flaw within the Interceptor X was not a weapon, nor a structural weakness in the wing spar. It was a microscopic architectural error in the electrical schematic, a demon hiding in the copper. The specific setting on the meter switch, often labeled GCU, test or simply position 5, was intended to close a circuit between the ground power unit and the cockpit indicators. It was designed to carry low amperage, just enough to wiggle a needle on a gauge so a mechanic on a rainy tarmac could sign off on a maintenance form. But the engineers had designed this circuit assuming a static environment. They assumed the aircraft would be cold, engines off, main generators offline, relying on external power carts. They had not accounted for what happened if that circuit was closed when the beast was awake. When the jet was airborne, the main engine generators were churning out massive amounts of raw AC power to feed the radar, the flight control computers, and the weapon systems. The electrical bus was a roaring river of energy. When a pilot, confused by turbulence or stress, accidentally rotated that small knob to position 5, he wasn't just checking a gauge. He was inadvertently opening a floodgate. He was creating a bridge between the high-voltage main bus and a low-voltage diagnostic loop that was never grounded for flight. The feedback loop. The moment the switch clicked into that detent, the resistance in the circuit dropped to near zero. The electricity did not flow to the gauge. Instead, it backwashed. It sought the path of least resistance, surging backward through the ground fault protection system. This phenomenon is known in electrical engineering as a parasitic load, but in this specific airframe, it was a parasitic predator. The massive spike in voltage bypassed the circuit breakers, which were too slow to react to the speed of the surge. The electricity traveled along the wiring harnesses that ran beneath the pilot's seat and along the spine of the aircraft. Crucially, these harnesses were bundled together with the control lines for the fuel boost pumps and the fire suppression system. It was a design choice made to save weight and space, bundling wires together as standard practice. But here, the insulation between the test wire and the fuel pump wire was insufficient to stop the arc of a high-voltage overload. The airborne fireball. The sequence of destruction was terrifyingly fast. It took less than 2 seconds from the moment the switch was turned. First, the surge hit the fuel pumps. These pumps were located inside the fuselage fuel tanks, submerged in thousands of pounds of highly volatile jet aviation fuel. Under normal conditions, liquid jet fuel is hard to ignite. It requires compression and atomization. But the fuel tanks were not just liquid. The empty space at the top of the tanks, known as ullage, was filled with explosive fuel vapor. The surge caused the pump motors to short-circuit instantly. The copper windings inside the pumps melted, flashing into white-hot sparks. Inside the fuel tank, simultaneously, the overload scrambled the signals to the fire suppression system. The onboard computer, flooded with contradictory voltage readings, interpreted the surge not as a fire, but as a sensor failure. It shut down the warning systems to prevent a false alarm. So, at the exact moment the spark ignited the fuel vapors, the plane's brain blinded itself. The resulting explosion wasn't a slow burn. It was a detonation. The pressure wave would rip the fuselage apart from the inside out. The cockpit floor would buckle. The wings, filled with fuel, would separate from the body. The pilot, sitting atop this eruption, was effectively riding a bomb that he had detonated with a flick of his thumb. Disasters in aviation rarely announce themselves with a trumpet blast. They usually begin as whispers, anomalies that are dismissed, quirks that are ignored, and gremlins that mechanics cannot reproduce. In the early months of the Interceptor X deployment, the squadrons were plagued by these whispers. The pilots were the elite, graduates of Top Gun and the weapons school, men with thousands of hours in Phantoms and Crusaders. They knew how a jet should feel. And they knew something was wrong with this one. During training sorties over the Nevada desert and the Atlantic test ranges, reports began to filter back to the base commanders. They were disjointed, bizarre reports that didn't seem to form a pattern. One pilot, returning from a night intercept drill, reported a flash bulb effect in his peripheral vision, a sudden, blinding arc of blue light from the fuse panel that vanished as quickly as it appeared. Another pilot, a seasoned major, reported that his entire HUD heads-up display had flickered and died when he reached to adjust his radio volume, only to reboot seconds later. Most alarmingly, a lieutenant on a solo flight reported the smell of ozone and burning insulation, the distinct, acrid scent of an electrical fire, that permeated the cockpit for 10 seconds before dissipating. The wall of denial. On the ground, the maintenance crews were baffled. They would tow the jets into the hangars, hook them up to the diagnostic computers, and run every test in the book. They would rotate the meter SEL switch again and again. Nothing happened. The needles wiggled. The lights blinked. The system worked perfectly. Why? Because the jet was on the ground. The main engines weren't turning. The massive electrical load of flight wasn't present. The sneak circuit was dormant, sleeping until it was fed the high voltage of the sky. This led to a dangerous culture of denial. The engineers blamed the pilots. "You're seeing things," they said. "It's glare from the canopy. You're imagining the smell." Commanders, under pressure to get the new, expensive jets combat ready, sided with the engineers. They scrutinized the pilots. Was it stress? Was it a lack of familiarity with the complex new cockpit? There were whispers that the pilots were spooked by the high performance of the machine. Then came the theories of sabotage. This was the height of the Cold War. Security officers began to shadow the ground crews. Had a Soviet agent infiltrated the assembly line? Was someone cutting insulation on the wires? The paranoia grew, but it was directed outward, searching for a human enemy, rather than looking inward at the blueprint. The day the sky cracked, the whispers turned into a scream on a clear Tuesday morning in October. Captain Mark Hojo Henderson was flying a routine perimeter patrol. He was a steady hand, a pilot known for his technical precision. He was flying at 25,000 feet, cruising speed, in a clean configuration. There were no enemies, no bad weather, no stress. The telemetry data recovered later would tell the story that Henderson could not. At 9:42 a.m., Henderson radioed that he was experiencing a minor fluctuation in his fuel flow indicators. It was a nuisance, nothing more. "Base, I'm going to run a quick circuit check," Henderson said. His voice was calm. He was doing exactly what he had been trained to do. He was going to troubleshoot the problem using the onboard diagnostics. He reached down. He found the meter SEL switch. He intended to check the generator output. But in the vibration of flight, or perhaps just a simple human slip, he rotated the knob one click too far. The radio transmission didn't end with a sign off. It ended with a sharp intake of breath, followed immediately by a sound that the tower controllers would never forget, a static-filled crack, like a thunderclap trapped in a tin can. On the radar screens at air traffic control, the single green blip representing Henderson's jet didn't spiral down. It didn't turn. It simply blossomed into a cloud of debris. 1 second, there was a $30 million aircraft. The next, there was a shower of aluminum confetti falling toward the ocean. The rescue crews found very little. There was no mayday, no ejection seat beacon. The disintegration had been so violent, so instantaneous, that Henderson likely never knew he had died. The Air Force grounded the fleet immediately. The sabotage theories vanished. They knew, with chilling certainty, that the plane had killed him. But as the investigators sifted through the floating wreckage, they still didn't know the most terrifying part. Henderson had killed himself, and he had done it with a button that was supposed to help him. The investigation into the disintegration of Captain Henderson's jet did not begin in a laboratory, it began in the ocean. For 3 weeks, salvage ships trawled the cold, choppy waters where the radar blip had vanished. They were fishing for ghosts. They brought the wreckage up in dripping, twisted pieces, shreds of titanium skin, shattered avionics boxes, and lengths of charred wiring harness that looked like the blackened nerves of a dead giant. These fragments were transported to a secure hangar at a remote Air Force testing facility, a place where the air always smelled faintly of kerosene and rust. Here, the crash investigators took over. In the grim parlance of the aviation world, these men were known as tin kickers. They were a breed apart. Engineers with the souls of coroners, men who could look at a piece of melted slag and tell you the temperature of the fire that consumed it. They began the agonizing process of reconstruction. On the concrete floor of the hangar, they laid out the debris in the rough outline of the aircraft. It was a 2-dimensional skeleton of a 3-dimensional tragedy. The focus quickly narrowed. The engine fan blades showed no sign of bird strike. The missile rails were intact, ruling out an accidental ordnance detonation. The flight data recorder, miraculously recovered from the seabed, offered the final clue. It showed a sudden, massive spike in the electrical bus voltage milliseconds before the recording ended. It wasn't an engine failure. It wasn't a pilot error. It was a heart attack. The Iron Bird. To prove their theory, the investigators couldn't risk another pilot's life. They turned to the Iron Bird. The Iron Bird was a torture rack for airplanes. It was a full-scale hydraulic and electrical mock-up of the fighter, stripped of its skin and bolted to a steel frame in a windowless laboratory. It contained all the guts of the jet, the pumps, the computers, the miles of wire, exposed for scrutiny. The lead investigator, a man named Cole who had seen too many crashes and slept too little, stood before the cockpit of the Iron Bird. He held the maintenance logs from Henderson's flight. He knew the pilot had reported a gauge fluctuation. He knew the pilot had tried to run a diagnostic. Cole climbed into the seat. The technicians powered up the rig. The generators whined to life, simulating the massive electrical load of high-speed flight. Simulating altitude, 25,000 feet, a technician called out. Bus be you're hot. Cole looked at the right console. He looked at the meter SEL switch. It was such a small thing. A piece of plastic worth perhaps $5. I'm going to cycle the meter, Cole said into his headset. Moving to test position, he reached out. His hand didn't shake, but his heart hammered. He rotated the knob. Click. The spark of recognition, the reaction was instantaneous. In the lab, there was no explosion. The fuel tanks of the Iron Bird were filled with inert testing fluid, not Jet A. But the violence of the electrical failure was visible. On the monitoring consoles, red lights cascaded like a falling row of dominoes. Alarms screamed. Sparks showered from the breaker panel behind the seat. Shut it down. Emergency cutoff. Smoke curled from the wiring loom near the floor. The data printout confirmed the horror. When the switch hit the test detent under load, it didn't just check the gauge. It sent a 115-volt, 400 Hz spike directly into the fuel management computer. The investigators stared at the data in stunned silence. They realized with sick clarity what had happened to Henderson. The spike had caused the fuel pumps to arc inside the vapor-filled tanks. The plane hadn't just broken, it had been turned into a flying fuel-air bomb. The trigger wasn't an enemy missile. It was a diagnostic check. The briefing room silence. The news had to be broken to the men who flew the machine. The briefing took place on a rainy Thursday. The squadron was assembled in the amphitheater. These were men who prided themselves on their courage, who accepted that death was a possibility every time they lit the afterburners. They feared surface-to-air missiles. They feared mid-air collisions. They feared G-induced loss of consciousness. They did not fear their own dashboard. The wing commander stood at the podium. He didn't use euphemisms. He put a diagram of the electrical system on the projector screen. He pointed to the meter SEL switch. "Gentlemen," he said, his voice devoid of emotion, "we have found the cause of the recent losses." He explained the sneak circuit. He explained the arc. He explained that Captain Henderson hadn't made a mistake. He had simply followed a procedure that was lethal by design. The room went dead silent. It was a silence heavier than grief. It was the silence of betrayal. "You mean," a captain in the back row asked, his voice trembling with suppressed rage, "that if I check my battery voltage while I'm turning, I blow up?" "Essentially, yes," the commander replied. The pilots looked at each other. They looked at their hands. They realized how many times they had casually brushed past that switch, how many times they had been 1 inch away from vaporization. The cockpit, once their sanctuary, suddenly felt like a trap. One pilot later described the feeling. It was like finding out your parachute was packed with anvils. It shattered the one thing a pilot needs more than fuel: trust in his machine. The order went out immediately. It was a red stripe message, the highest priority in the Air Force logistics chain. Across airbases in Europe, Asia, and the continental United States, the result was the same. The roar of engines stopped. The flight lines fell silent. The most advanced interceptor in the world was grounded, defeated not by the Soviet Union, but by its own copper wiring. The immediate fix was crude, almost insulting in its simplicity. Since the switch could not be easily rewired without ripping the entire aircraft apart, a process that would take months, the Air Force opted for a physical barrier. Mechanics descended on the cockpits with drills and rivets. They installed guards, small metal cages or heavy-duty locking plates, over the meter SEL switch. In some squadrons, where metal guards weren't immediately available, the solution was even more primitive. Crew chiefs used high-strength speed tape, aviation-grade duct tape, to physically bind the switch in the off position. They placed placards on the instrument panel in bold, red letters. Warning. Do not operate meter selector in flight. It was a humiliating bandage on a multi-million-dollar wound. The surgery. The permanent fix required a massive mobilization of engineering talent. The entire fleet had to be retrofitted. The jets were pulled into hangars, their panels stripped away. The sneak circuit had to be physically excised. New relays were installed to isolate the ground test circuits from the flight power bus. Circuit breakers were upgraded to fast trip models that could sever the connection faster than a spark could ignite the fuel. Manuals were rewritten overnight. The pages describing the in-flight electrical checks were torn out and replaced with warnings. Simulators were reprogrammed to teach pilots a new muscle memory. Keep your hands away from the right console unless absolutely necessary. The cost was astronomical. Millions of dollars were poured into fixing a mistake that should have been caught on a drafting table years before. But the cost in blood had already been paid, and that was the currency that mattered. The long shadow. Eventually, the red stripe was lifted. The engines roared to life again. The jets took to the sky, their sleek silhouettes once again patrolling the edges of the atmosphere. Technically, the aircraft was now safe. The bomb in the button had been defused. But the relationship between the man and the machine had been permanently altered. The Interceptor X went on to have a long service life. It set speed records. It won conflicts. It was a marvel of aerodynamics. Yet, its reputation never fully healed. Among the fraternity of pilots, the story was passed down from instructor to student, a grim fable told in the office's club bars. Watch that panel, the veterans would warn the rookies, pointing to the scarred spot on the console where the switch sat behind its metal cage. She's fast, and she's mean. But remember, she's got a temper. If you touch her in the wrong spot, she'll kill you. The fighter jet became a symbol of the Cold War's technological hubris, a reminder that in the rush to build the fastest, highest, and deadliest machines, the engineers had forgotten the fragile human sitting in the center of the storm. The legacy of the Interceptor X was not just its kill ratio or its top speed, it was the cautionary tale of the switch that proved that sometimes, the most dangerous enemy is the one you bring with you into the cockpit.